All right, so when we left off, we were talking about work done at the moving boundary of a simple compressible substance, and we said that normally we say that work is the integral of f dx, going from, say, position 1 to position 2. But that's not really the sort of work that we usually are doing in our thermodynamics problems. So if we consider pressure to be force per unit area, then force is pressure times area, and that ends up simplifying to work as the integral of P dV. Now, one of the things that we know from, say, Calc 1 is that this is equivalent to considering drawing the curve of how pressure goes from state 1 to state 2, and this is the area under the curve. And so, for instance, if these are the same 2 points, P1 and P2, V1, V2, here and here, but one time my curve goes this direction, one time it goes this direction, the area under the curve will be very different. And so work is path dependent. It depends on how pressure and volume are related. And so we write that with this squiggle D delta symbol instead of a normal block letter D like we do here in volume. Now let's look at some possible processes that we could consider. So first, let's look at a constant pressure process, also called isobaric. We're going to look at this one first, partly because it's common. Almost anything that's done in a system that is just open to the atmospheric pressure, that would be called constant pressure. Also, we're looking at this because mathematically it's simple. If I integrate this from state 1 to state 2 of P dV, but P is a constant, I can bring it out. And so we're just looking at the volume change from state 1 to state 2. So pressure times the volume change is the work for an isobaric process. Well, what are some other common processes? An isothermal ideal gas is another one we'll look at fairly frequently. Now, I do need it to be an ideal gas, but constant temperature process with this ideal gas. So P, well, PV equals MRT. Then P is MRT over V. I can put these things in, but mass, if it's a closed system, is constant. R, the gas constant, is constant. And temperature, well, I said it was isothermal, so the temperature is constant. These all come out. Now I just have dV over V. That's the natural logarithm of volume. Natural log of state 2 minus the natural log at state 1 simplifies to be the natural log of the ratio at state 2 over state 1. And so for an ideal gas that's isothermal, I could use this expression to calculate the amount of the work. How about a polytropic process? Now, a polytropic process is going to be any process where I can say that pressure times volume to some power is constant. Okay, now that power there's going to be called my polytropic index. And this is sort of an odd one. Now, whenever n is not equal to 1, I can integrate this by solving for V to a power is a constant over the pressure. Okay. Or P is the constant divided by V to that power. And I can use that to substitute into the integral. And with a little bit of algebra, I would get that the work is PV minus PV at those two states divided by 1 minus the power n. If n is equal to 1, then I end up with the same expression as I did for the ideal gas law. So this does not require it to be an ideal gas, although we'll find that this frequently is when I'm going to be able to apply it. But this just simply requires me to have something where I know that pressure times volume to a power is constant throughout the process. Now this is sort of an odd little expression here. I'm going to derive this in a separate video that you can choose to look at. But you can also just take my word for it or read in the textbook. So let's look at an example. So I have a gas compressed from 14.5 psia and 0.24 cubic feet to a volume of 0.04 cubic feet. It's a quasi-equilibrium process, meaning that these rules all apply. And it's polytropic with an index of 1.33, and we want to figure out how much work there is. Now, I haven't said anything about whether it's an ideal gas or anything like that, so I can't use those rules, but I know it's polytropic with n equal 1.33. So if I do that, then I can take PV to the powers, okay? P2 is therefore P1 times V1 to the 1.33 divided by V2 to the 1.33. Now, if V1 and V2 have the same units, okay, then that will cancel out the units here, and the pressure units will be the same for the two. So 14.5 times 0.24 over 0.04 to the 1.33. Be sure you do know how to do this on your calculator. I find that sometimes people haven't done these crazy powers on their calculator before, and then they end up getting strange answers. So check on this and make sure that when you do this calculation, you get 157 psi. Now, that tells me what the pressure is, but I want to know the work. So I'm going to take this pressure times that volume, V2 is 0.04, subtract P1, 14.5, times the volume 1, 0.24, divide all that by 1 minus 1.33. Now, my units, what are the units here? Okay, a psia is a pound force per square inch. My units on my volumes are cubic feet. So I need to convert my inches squared to feet squared, and that will give me foot-pounds force, which are the appropriate units for work. So I end up pushing buttons on a calculator using this conversion factor, negative 1224 foot-pounds force. So we're going to take a break right now and come back with another video.